Okay, awesome. Thank you so much. So let's get started. So my topic for the presentation is complexity in recommendation systems. I'm Nishan Subedi. I head algorithms and I'm a VP of technology at Overstock. Cool. So the goal of this presentation is to highlight the complexities with long-running recommendation systems in production, and highlight some of the approaches to mitigating some of these complexities that exist and arise, and experimentation practices that help us iterate on our recommendation systems better. To roughly outline an architecture and talk about similarities with learning to rank as an approach to recommendation systems, and talk about some of the ecosystem effects of recommendations. So a quick introduction to Overstock for those of you that are not familiar. Overstock is a marketplace specializing in home goods, and we have roughly 50 million monthly visitors. We've been around for 20 years. We've had a recent push towards machine learning, and we're growing quite a bit recently. I am the head of algorithms, and I am a VP of technology here. The products that I lead include the organic search from the user interface, the backend systems, the machine learning systems, to the ads platforms. This includes the auction, the ranking, as well as the partner interface, our recommender systems, and we have multiple different carousels that we serve recommendations on. Pricing science, which determines pricing for products inside of Overstock. A lot of forecast and estimate delivery models. Previous to this, I was a scientist at Etsy working on ranking, as well as I've worked in systems engineering in the past. So briefly, I wanted to touch on complexity, and the point I want to make here is that recommendation systems, when you have many of them, veer towards complexity as systems, and there are certain inherent properties about complex systems that manifest themselves in recommendation systems. So particularly of note are feedback and bias. A lot of recommendations algorithms are trained on user feedback, and so this makes them sensitive to position and presentation bias, right? Like, people don't engage with things that are not presented to them. And in addition to this, the features that we leverage, a lot of times historical features perform pretty well for the algorithm, but these help reinforce a lot of the biases that exist in recommendation systems. And the other is one of emergence. This is behaviors that slowly start manifesting themselves, or like user trends and patterns that they start getting used to because of certain properties in the recommendation systems or your systems at large. And so these tend to veer away from the original design of the recommender systems, and so this is something to be careful of, as well as long-term effects of having these systems in production. Over years, like, priorities shift and focus changes, so the systems and the data and features that get passed into the system slowly start deviating towards not intended behavior, or like slightly different behavior. Your user profile, user base changes, so the kinds of optimizations that might have been valid when they were tested may slowly move towards unoptimized states over time, and that's something to be mindful of. In addition to this, ML debt makes some of the problems of managing them over long periods of time particularly worse. Specifically, things like entanglement, which is a lot of times the features end up muddling up effects across different systems or algorithms. One point of note here is when you're running A/B tests and you're training your data on both control and test variant, you'll find your algorithm is learning from the other side, so your test may not be well flushed out. In addition to this, a lot of times during feature engineering, there's a lot of dependencies that implicitly creep up, and changes to any one of these data sources may not be monitored or logged completely, which can have drastic downstream effects on the performance of the algorithm. And on top of this, feature erosion is effectively like the meaning and the quality that went into a particular feature may get lost over time as these systems changes, and a lot of times it's very difficult to quantify or even detect these kinds of feature erosion happening. In addition to this, when you have multiple learning algorithms, they can kind of be considered agents that are learning in the environment, and so all of these lend recommendation systems towards becoming complex systems. And complex systems are fairly well studied systems. They range all the way from information theory to biological systems to informational systems, and so it's worthwhile treating our recommendation systems as complex systems and understanding and navigating the challenges that come with complexity. Another difficulty that arises because of this is your measurements may not generalize. What I mean by that is you may run an A/B test to measure a particular performance, but over time that same performance is not necessarily valid anymore because of a shifting landscape, because of the users involved on your platform or the different systems that interact with one another. So this kind of leads us going a little bit deeper into challenges that arise with experimentation and measurement. A lot of times, ideally, we want to run holdouts to be able to measure the long-term effects of an algorithm, but these are very expensive from an engineering standpoint, because you'd have to, at the very least, maintain these two systems as well as everything that is required to power them. Proxy metrics are difficult to find, and oftentimes there is a fidelity loss in your proxy metrics, which is to increase conversion in an online setting. Let's say you want to improve how many things people buy on your platform. You might use some offline measurement of that metric to optimize your algorithm, but there is usually some discrepancy between how you've crafted your offline metric and how that translates to the actual business KPI that you're measuring. And this is, so the next point is specific to recommendations and discovery oriented platforms. Oftentimes we talk about hard being the right kind of metrics to improve on. So this is customers' happiness, customers' engagement with your platform, how much they adopt your platform, how much they stay on your platform, and whether they're able to get the task they came to your platform with done. These metrics become really hard to measure for recommendation systems, because certain actions, depending on the context or the user's general time frame, may or may not translate directly to one of these metrics. So for example, for engagement, if someone is going to the search bar repeatedly after having shown a particular treatment recommendations carousel, it's not straightforward whether this means they're now inspired for a new journey and are engaging because it's a desirable trade, or they're engaging because they're no longer able to find the things that the recommendation system would have provided them otherwise. The other challenge is heterogeneity in treatment effects, and this basically means every user is kind of different, and usually with recommender systems, a large value that they provide is being able to cater to each user's specific needs, but then it becomes very difficult to isolate and even detect the differences in populations as you're testing your experiments for them. In addition to this, there are a number of market effects that may arise based on the constraints in your platform. One area where this is very obvious is in an ads platform or a sponsored platform of sorts, where there is a budget that goes in, that is allocated for these products. And so if you find yourself depleting the budget from a particular control group, let's say, or a treatment group, it ends up affecting the other side as well. The other place where this is really obvious is for products that are in stock on a limited quantity, you might find that one treatment group is particularly good at selling those products or kind of getting through the stock, and so that affects your measurement on the other side as well, which imposes unique challenges for measuring your experiments. And in addition to this, there's a number of interaction effects where your changes may have unintended consequences to other kinds of parts of your platform, and they may not be easy to detect and measure. So, and the last one we come to is a lot of times, because we're constrained in how long we can run these experiments for. If you're running for a week or two, what you might be measuring is a model's ability to learn quickly, but not necessarily how it's going to perform on a long-term basis. So an algorithm might learn quickly, but over the long run may not be as ideal as some other algorithm, and they're not usually uncovered by the A/B test we run. So I wanted to kind of next move on to a general outline of a recommender system, and you'll notice the slide here is that of a production ranking system. Oftentimes, there is quite a bit of overlap across these systems, especially when you have multiple number of different algorithms. Like at Overstock, we have at least 10 to 20 different algorithms powering recommendations and search, and so you find that it's the pipeline ends up being very similar across all of these. So multiple recommendations algorithms are driven off of just similarity across either a vector representation or some representation of sorts. It's very similar to recall from an inverted index like solar, and I'm referencing the bottom left portion of the diagram here. On top of this, you might apply some layers of re-ranking on top, and there's usually a query processing associated with it. And for this thing, the query is not limited to just a keyword query that a user provides. It could be the user itself, right? So the user could be what we query off of. It could be the entities that you want to display off of, which is mostly what recommendation systems drive. And so, and it could also be the context of where the user are on their journey. So all of these kind of add up to the context and the query you're providing your recommender systems. And you might have some framework for your A/B tests on top of that, as well as a model and associated features. So once that online system gets engagement, all of that feeds into the server logs that end up being features that end up on the model. A pretty important point to note here is simulations, tests, replays, offline metrics that you have. These are essential parts of what comprises a recommendation system. So as you'll notice, I've formulated the previous recommendation system as a learning to rank system. And this is definitely a trend in terms of where the industry is growing. In this slide, I've borrowed two diagrams, one from a system from Facebook and one from YouTube. And the bottom one talks about embeddings-based retrieval as a general retrieval system, not just for search, but for a recommendation system as well. And the top one is combining different embeddings into an optimization task and then a real-time embedding, and that comes off of a YouTube paper. So kind of the benefits of formulating your recommendation system problem as learning to rank is you can apply re-ranking layers, which is a well-studied area of research. You can have retrieval based on embeddings and productionize them in a generic way. You can model the user and your entities as embeddings, whether it's in the same space or different spaces that you've learned interactions amongst. You can optimize recommendation systems as for specific goals, and this becomes of critical importance when you have a number of different recommendation systems and algorithms, and they all they're based on where they are in the user journey, need to provide for different goals. This formulation also allows for quite a bit of synthetic training data, and there's large bodies of research that are emerging now in terms of effective training techniques. A lot of them have to do with being able to generate synthetic training data from the user logs that exist. And then these tackle biases in multiple different ways as well as being able to leverage session information in a consistent and holistic manner. So, so this is an example of kind of some of the recommender systems that power Overstock. So for any given user, we send them emails for what we recommend them. On the homepage, we have a things we know you'll love carousel. Going into a specific product page, we have similar item comparisons. We have similar items in that particular taxonomy. We have products we feature for various reasons, as well as top sellers associated with it. So this point I want to highlight like a change in thought from looking at a particular recommender carousel or a system as one entity you're trying to solve for, to a shift towards thinking of the entire ecosystem that your recommender system lives in. I think this is becoming more and more important as recommender systems become the bread and butter of a lot of discovery-oriented tasks that users engage on your platform. So for any kind of platform, technical platform today, there is multiple touch points in the funnel, from making your users aware of your platform to getting them to become loyal customers. And it's critical at this point to be able to consciously and intentionally model each of our recommendations for each specific touch point on the user's journey. And kind of that leads me to personalization. This has been a hot topic in the industry for a while now, but there's a few key tenets that I think make personalization effective. First is like the user doesn't know all the different technical components that lead into what goes into building your platform, right? So from the customer's perspective, they're somewhere on their journey, and your platform just happens to be one area in their kind of use case in fulfilling the need they have. And it's important for us to realize this and build our systems that support them in their user journey. And so consistency is at this point table stakes in terms of being able to serve their needs better. That means knowing where they come from, knowing roughly what tasks they're trying to solve, and orienting your systems to provide for those better. This becomes a lot easier when we have a consistent user representation that's leveraged across all the different algorithms, a unified practice to training and productionization, so you don't waste a lot of time on that, using signals across multiple different platforms so that they are aware of and can account for each other, and also factoring the stage that the user is in their journey. In addition to this, incorporating the context of where they landed from, because oftentimes that carries a lot of essential information in terms of where they're going to go next. So that's kind of a wrap up of my prepared slides. Thank you so much. If you want to follow up with me, this is my LinkedIn. Please reach out to me there, and I'll open it up to the floor for questions. Thank you. Sorry, I was not able to make the slides bigger. What is the research paper you mentioned in the Facebook embeddings? Yeah, so the Facebook one, there's a link to it in the slides, and I'll make the slides public, so you can find it in my slide share, most likely. The paper is, I believe it's called Real-Time Evaluation, Embedding-Based Evaluation. So let me actually really quickly find a link to it. Real-time data processing. There is a link to it, but I will drop it right here. So it's called Embeddings-Based Retrieval in Facebook Search. And Facebook actually has like a couple of really good libraries for embedding-based approaches as well. And the other one on the same slide. So that comes from YouTube, and this is a slightly older paper. This is effectively talking about a sparse dense network. And if you look at some of the work that's been done on TensorFlow, there are plenty of examples about this architecture. And this is one of the simpler deep learning architectures to follow. You're welcome. Any other questions? Well, thank you so much for joining. I'm glad you could be part of this presentation. Again, reach out to me if you have any specific questions. Always happy to talk about this. Hope you got something worthwhile out of this presentation.